Hello students. So good evening all of you. So can you all see the screen clearly and can you hear me? So please do type in the chat box. Can you all see the screen clearly? And can you hear me? Yes? Okay, fine. So let us quickly recollect the past 4 lectures that we discussed on this first module, fluids and its properties, correct? So yeah, good evening. Fine. So in the first lecture we have seen what is the difference between a solid and a fluid, correct? So we have seen solids are the substances which can resist some shear stress with some finite deformation, of course in static state, correct? And fluids are the substances which can't can't resist any shear stress in static state, correct? So basically a fluid is a substance which deforms continuously under the action of infinitesimally small shear stress. This is what we have seen clearly, correct? And since the deformation is continuous in case of fluids, we have seen in case of fluid mechanics we deal that shear stress acting on any layer of fluid is directly proportional to the rate of shear strain, correct? And we have also seen in a particular case of linear velocity profile, this shear strain rate is proportional to velocity gradient or equal to velocity gradient, correct? This is what we have seen. So can you all recollect this first lecture that we discussed? So basically in the second lecture we have seen what is this Newton's law of viscosity, and also we have moved on to what is the classification of fluids basically, correct? So after classification of fluids we have seen different cases of viscosity, and also we have seen different cases of viscosity, and then we have also seen what is compressibility of a fluid. Good evening all of you. Good evening Suya, Suyendra, Kapil, Shriya and all. So can you all recollect all these first 4 lectures? So basically in the 4th lecture we have seen various cases of Newton's law of viscosity, means basically when a disc is placed on top of an oil, then what is the viscous torque that is required to overcome this friction, and also we have seen what is the power that is absorbed within this viscous fluid, correct? We have seen all these things, and after that we have also seen compressibility, and the concept of compressibility we have seen like basically what is the difference between compressibility of a fluid and compressibility of a flow. There are 2 different things, correct? Good evening Vamshi. So please, yes, good evening Rahul. So please see here. So can you all recollect the difference between compressibility of a fluid and compressibility of a flow? Yes or no? So if you quickly recollect, in compressibility of a fluid we define something called the coefficient of compressibility, where this is equal to, of course, your dp divided by your minus dv by v volumetric strain that occurs for this for a unit change applicable in pressure. Okay? This is what we have seen in compressibility of a fluid, and in compressibility of a flow in yesterday's class we have seen for any flow whose Mach number is less than 0.32, we can assume this flow to be an incompressible flow. Okay, we have seen how this 0.32 is coming here. So we have seen some derivation actually. So it's not actually a derivation, it's just some basic idea on that tells us how when for what mathematical conditions we can treat the flow as incompressible flow and of course a compressible flow. So are you all clear till this point? This is the point where we have done till yesterday. So are you all clear till this moment? Depending on this value of k, this k speaks about compressibility of fluid, and this Mach number is something that talks about compressibility of flow. Correct? Yes? So please do respond. Is that clear to all of you? So can you all recollect all these things from yesterday's lecture? Yes or no? So please do respond. Can you all recollect this from yesterday's lecture? All of you? Yes. So if that's the case, then let us move on to today's topic. Concept of surface tension. One very important concept as far as interviews are concerned and also some questions are concerned. Okay. So see here. Let us try to identify the concept of surface tension in today's class. Concept of surface tension. And we will see why this name surface tension is also given for this particular physical phenomenon. Look. Okay. Fine. So we are clear till here. So let us identify why this concept is named as surface tension also. Okay. So see here. Let us suppose there is some liquid, bulk of liquid that is here. There is some bulk of liquid. Some bulk of liquid. Okay. Now see carefully. This is some bulk of liquid. Let us identify what is surface tension and how surface tension is quantified. Let us see carefully. If this is your bulk of liquid, then you know if this is your molecule here, then you know molecular forces are basically 2 types: cohesive forces and adhesive forces. So cohesion means basically cohesion is between similar molecules or same kind of molecules. or same kind of molecules, and adhesion. Let us suppose if you are talking about adhesion, then this adhesion forces or adhesive forces are generally between different molecules or molecules of different substances. Okay. Now, for example, if you see your Fevicol is an adhesive because Fevicol sticks to different substances, but we can't stick Fevicol with Fevicol, correct? Because that never happens, correct? Even in ads that you see. So Fevicol is basically an adhesive. It's used to stick to other substances, which is not Fevicol, correct? So this cohesion forces are the forces which are in between same molecules, and adhesive forces are something that are between molecules of two different substances, correct? Now, let us see what happens. If you take a molecule here, then this molecule is subjected to some cohesive forces from this molecule. Similarly, from this molecule which is here, from this molecule which is here, from this molecule which is here, similarly here, 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 and also here in this case. Which means, can you understand one thing? If you take any molecule here, let us suppose you are taking some molecule here. This molecule will be attracted by all surrounding molecules with some equal amount of cohesive forces. Yes or no? Can you identify this? Can you all identify that if you take some molecule here, this molecule, because of this cohesion forces, this molecule is attracted from all other surrounding molecules by some equal amount of cohesive forces? Yes or no? So please tell me. Please tell me this. Can you all understand this? Now, see carefully. If you put all these molecules in a space or region, then you form a sphere, and this sphere which you are writing here is called, sphere of influence. You can see here, sphere of influence. Sphere of influence means this molecule which is in the sphere is influenced by all other molecules. Similarly, if you take any other molecule here, in this case, let us suppose this is the molecule, then again there is some cohesion forces from all other molecules which are surrounding it, correct? So we have some sphere of influence once again, correct? So this is the case, we have one more sphere of influence. But now if you take the case of these molecules which are here on the surface, let me extend this surface a bit. Okay, so now see carefully. Let us suppose we are talking about some molecule which is lying here, and let us suppose on the top of this we have air, and let us suppose this is some fluid, basically your water, okay, and at 20 degrees Celsius around. So now if you take care of this molecule, then this molecule is subjected to the cohesion forces by these molecules which are adjacent to this on the layer. Similarly, this molecule is also attracted by the downward molecules in these different directions, of course within the fluid. Now, can you understand one thing, that if this is your region which this molecule is being attracted, and if this is A on the top, let us suppose there is some air on the top, and you know cohesion forces are generally strong as compared to the adhesive forces. So generally, can you understand that the forces exerted by the adhesive forces exerted by this air on this water will be very less? Yes or no? Can you all understand? Look, this is very important concept, so please listen carefully. If this molecule which is on the surface is pulled by all other molecules at the bottom, and if the adhesion forces between air and water is less, then can you understand that this layer or this molecule, in fact, if you take a layer, a bulk of fluid which is out of the board to some extent, then every molecule on this top layer which is perpendicular to this board, every molecule on the top of this layer is subjected to some pulling by the downward molecules. Yes or no? Please tell me, did you understand this? Let us suppose if this is a molecule on the surface, then all the molecules which are here are trying to pull the surface. Yes or no? Yes? I need responses from all of you students, so please do respond. Please do type in the chat box. Are you all able to understand this? I need responses from all of you, so please do respond. Please do type in the chat box. Correct? Yes. Shubha, Manan, Kapil, yes. So see here, if these molecules are, yes, correct? So if these molecules are trying to pull, then see carefully. This is the case with every molecule on this surface. This is the case with every molecule on this surface. Now, if this is the case, can you experience that this free surface which is here, generally you denote this free surface like this. So this free surface which is here, is acting like an elastic membrane. Correct? Let us suppose you have a polythene bag here, and if I am pulling this polythene bag down from all the things, elastic membrane, let us suppose This is elastic membrane. Okay, because you know the viscosity of this air is a bit less as compared to this, and of course at the interfaces definitely this coefficient is more. Okay, so in this case, if this free surface is acting like a polythene bag, and if I am pulling the polythene bag at different points towards down, then will this free surface is subjected to tension? Yes or no? Because it starts stretching. Let us suppose I have a polythene bag on my hand, and let us suppose I am pulling this polythene bag down from all the sides. Okay, from all the sides. Then will this polythene bag on my hand suffers tension in all directions? Yes or no? Correct? If I am pulling this, it suffers tension and it starts stretching out. That means this surface which is here is under tension. It's under tension forces. Correct? So now, if you take a layer of molecules which are perpendicular to the board, so if you take a layer of molecules which are perpendicular to the board, then every molecule on this layer, like 1, 2, 3, 4, 5, every molecule on this layer is subjected to some tension. So if you draw the top view of this now, this is the free surface when viewed from the top view. Okay, so this is the free surface which you are viewing from the top view. So if you take a layer which is perpendicular to this, which means if you have some layer like this, then at every point on this layer there is some tension. Correct? There is some tension. There is some tension forces that are acting on this surface. And this force which is acting on the surface is called tension force. And of course, if this is of length L, to quantify this, if this is the total force that is acting, then your sigma is nothing but this surface tension force. The surface tension force, you remember you try to understand the name. The surface tension force means the tension force that is acting on the surface of the liquid. Means if these are the different molecules at different locations on the surface, then there is some tension force that is acting on the surface, and the surface tension force per unit length is called your surface tension. And this is a property because it's independent of the length when you are dealing per unit length. Are you all clear? Did you all understand what is surface tension clearly? The surface tension force that is acting on the layer of fluid, on the free surface of the fluid per unit length is called surface tension. Are you all clear with this definition? Sigma is equal to F by L. Yes or no? This is the top view of this plane. If you look it from the top, then definitely there exists some layer of molecules which are subjected to some stretching on both the sides. Correct? So definitely this force per unit length can be called as surface tension. Is this concept clear to all of you? Is this concept clear to all of you? So please do respond. Yes. Very good. So this is sigma is equal to F into. Yes, tension do acts, but if you take on the surface, then definitely this surface which is here is subjected to some stretching. Okay, so that's why this is the surface tension that's acting on this top free surface of the liquid. Okay, so see here. Now, so one thing is very clear. So whenever you're having some bulk of liquid, then whenever you're having some bulk of liquid, then if you are having a molecule here, then this molecule is subjected to some tension, correct? Some imbalance of forces because of some imbalance of forces. Let us try to draw this a bit clearly. So this molecule which is here, let me emphasize this for you. Then if this is air and if this is water, then this molecules which are on the surface at every point are subjected to some imbalance in its forces, correct? So now look carefully. If you take any molecule here, then you have seen there is some sphere of influence which is such that every molecule within this sphere of influence exerts some cohesive forces on each other. Now see carefully. If I want to bring this molecule here, look, if the molecule which is initially here, if I want to bring this molecule onto the top of surface, should I do some work against this cohesion forces of other molecules? Tension because of what? Adhesion or cohesion? Due to both. Surface tension is a binary property. Of course, I'll come to that later. So see here. So please see carefully. There is this molecule. This molecule is actually under the action of all surrounding molecules. Now, if I want to move this molecule to here, means moving this molecule from this location to this location is nothing but forming a surface. Means if I want to form a free surface, that means I should do some external work against this cohesion forces. Is that clear? Yes or no? Please tell me. If I want to form a free surface, means if I want to move this molecule from this location to this location, then definitely I need to do some external work to overcome this cohesion effect of other surrounding molecules. Correct? Can you all understand till this point? So please do respond. Can you all understand till this point? Yes? Yes or no? So please do type in the chat box. Clear? Yes. Very good. So now let us continue. So see here. If this is the case, then the work that I am doing here, the work that I am doing on these molecules is stored as some energy within these molecules, and that energy is known as surface energy. Means the surface contains some energy which is actually the work done that is done to create this free surface actually, correct? So this is the physics behind this. So this work done that you do on this molecule means the work that you are doing on this molecule to move it here from this location to this particular location means to create a free surface. This work done is stored in these molecules as surface energy, and you know that energy is located at all the molecules at the surface. So that's obviously it's called as surface energy. Now what is the formula for this surface energy or work done? If you want to form a surface, if you want to increase the size of a surface, then what is the formula for this work done? This is the main interest. Now look here, let us suppose this is the top view, correct? Now you know work done can be written as force into displacement, which is delta x. Let us suppose delta x. Now you know this, whenever there is a set of molecules, then every molecule on this set is acted upon by some forces on either sides. You know this. You know this. If this is your total surface tension force F and this is your L, now this sigma is nothing but F by L. You have seen this, correct? Surface tension. Now see carefully. If I want to increase the size of this layer from this location to this, let us suppose I want to increase, let us use a different ink for you to understand. So see here, let us suppose the surface which is initially here, if I want to increase the surface to till this extent, for example, means if I want to lift this free surface by delta x, look, this is L, this dimension is L from the top view. Now if I want to know what is the force that I am applying, can I write this F as sigma into L? Sigma into L into delta x. Can I write this? Sigma into L into delta x. Look carefully. This length is L and I am moving this by delta x. Means if I am having this as L, then I am moving this L by delta x height. Correct? Now can we write this sigma into L times of delta x? What is this L times of delta x physically represent? Look, if you are having a thickness of L out of the board, then if I am having, see, let us suppose my palm is the thickness of the liquid layer which is outside the board, then if this location is L and if this is delta x, then can I say the total increase in the area of the surface is delta A, sigma into delta A, which is L times of delta x? Yes or no? This is your L, which is the horizontal dimension which is perpendicular to the board. So if I want to increase this surface layer from this location to till this point, then the increase in area that's happening is nothing but this L into this delta x, correct? Can you all understand that this L into delta x is the change in area for creating this free surface? Change in area that occurs when you create a free surface, when you extend a free surface? Yes or no? Is that clear to all of you? Can you all understand that this delta A is nothing but the increase in area while you are creating an extension for the free surface? Yes or no? So please do type in the chat box. Yes? Vamsi, look here. It's very simple. Look, this is the top surface of this liquid layer, correct? So if this length is L and if you are trying to increase this free surface by amount delta x, then definitely look, this dimension is L and this dimension is delta x, and if the fluid is continuously increased from this layer to this particular layer, then this L into delta x will be the total increase in this surface area, correct? So which means work done in creating a surface, work done in creating a surface, work done in creating a surface is equal to the surface tension force that's acting on the surface into change in area of the surface. Change in area of surface. Okay, so this is what we have. So let us highlight this point. Let us highlight this point a bit. Okay. Fine. So let us try to this particular block here. Now you got the idea. Okay, so this L into delta x, this L is of course the top view of this. So this is the work that you required in creating a surface, of course, whose change in area is delta area of the surface. Okay, so this is what we have. So now based on this, there are few mathematical questions, a few questions that come in exams, so you can answer them. Let us suppose there is some sphere. Let us suppose there is some sphere which is of radius r. Let us suppose this is the sphere of radius r. Now let us suppose this sphere means this is some droplet, and this is the area where you have cohesion between water molecules and also adhesion from air molecules, correct? So this is the region which is suffered to adhesion from air and also cohesion due to water. Let us suppose this is water, for example. Now let us suppose this big sphere of water is now dissociated into small droplets. Okay, so let us suppose this big sphere is now dissociated into small droplets. Maybe every droplet is of small size r. Okay, let us better not let us draw some manual sketches because it's difficult for us to create equal size. So see here, let us suppose this big water droplet which is initially here is split into small water droplets. Now, and let us suppose this complete big water droplet which is here is divided into or is split into n small droplets. N small droplets. So what is the work required in blowing up this big water droplet into some small n droplets of water? Okay, so let us see this. Just now we have seen work done in creating the surfaces is equal to, because by blowing this we are creating lot of free surfaces here. You see here, this is a free surface, this is a free surface, and also work done is equal to sigma into delta A. Sigma into delta A. Now, what is the increase in area from splitting up this big water droplet into small water droplets? You know one thing, mass has to be conserved, correct? Means if this big droplet is of having some mass, then definitely this mass has to be conserved here. So if you write that, you know mass is nothing but density into volume. So volume of big droplet should be equal to density into volume of small droplet. And of course, there are n droplets totally, so we have a multiplication with n. And you know, liquids are practically incompressible, so let us cancel this density because it's same on both sides. So this big volume, which is 4/3 pi r cube, this should be equal to n times of the small volume of the small molecule. And what is the volume of the small droplet? 4/3 pi small r cube. Means if every big droplet is split into small n droplets of radius r, smaller, then definitely this equation should get valid. And 4/3 pi, if you cancel on both sides, you have this r is equal to, or maybe you can write this, capital R is equal to n power 1/3 into r. This is what we can write here. Or else small r is equal to r divided by n power 1/3. This is the radius of each small molecule or each small droplet that gets split up, correct? So what is the surface area of this big water droplet, which is 4 pi r square? So let us write this. Sigma into change in the area is nothing but n times of surface area of all these small droplets, and you know n into 4 pi r square, because you know if this is a small droplet of radius r, then definitely 4 pi r square is the surface area, and totally there are n droplets, so n into 4 pi r square minus that big droplet area is 4 pi r square, correct? Can you all understand this equation? How did I write this? Basically, this R is associated from mass balance, and also this work done formula we are writing it from our previous analysis, sigma into delta in the area of the surface, and definitely this is equal to sigma into n times of 4 pi r square minus 4 pi r square. Are you all clear till this point? Are you all clear till this point? Did you all understand how this is coming? Are you all understanding the things? So please do type in the chat box. Are you all clear till here? Yes or no? So please do respond. And many times in exams, this n will be given as a cube number. Like for example, this is n can be given as 8, 64, 125 and all. So calculations come a bit easy here. Okay. Fine. Vamshi, Prithvi, Shubha, Madan Kumar and all. So see here. So this is equal to sigma into n times 4 pi. This small r can be written as capital R square by n power 2/3 minus 4 pi r square. This is what we have generally. So if you make the calculations, 4 pi r square you can take out. So sigma into 4 pi r square into n divided by n power 2 by 3, which is n power 1 by 3 minus 1. And generally when n is given as some big number like a cube numbers, they'll give in general to make your calculations a bit easy. So if n is 8 for example, then 8 power 1 by 3 is 2, 2 minus 1 will be 1. And of course this is the work done and it's of course positive. So you can see clearly this n, if it's as n increases, this complete value increases and the work done that you need to blow up these many droplets increases. So this work done is given by this. Now, okay, so let us go for conceptual points. See here, surface tension is a binary property. What is the meaning of this? Surface tension is a binary property. What do we mean by this? What do we mean by this? Look, normally I told you, in this case, whenever there is only water that is, or whenever the same fluid is surrounded by a molecule, will there be any surface tension at this location? First of all, is this a surface or is there any tension that's acting here on the molecule? So please tell me, is there, whenever there is only liquid, then can you please tell me, is there any surface tension that's acting at this location? No, there is nothing. Similarly, if you take only in the air, if you take any molecule in the air and if you try to observe the cohesion forces and all in all directions, then can you tell me, will there be any surface tension within this location? Yes. So please tell me, will there be any surface tension within this location only when you take air into consideration? No, there won't be any surface tension. But for having this surface tension, there should be some imbalance between the cohesion forces and the adhesion forces suffered by the molecules. Correct? That happens only at the interface. For example, if you see this diagram clearly, at this location means in the vicinity of this, here there will be some this imbalance of cohesion and adhesion forces. Correct? So this means for having this concept of surface tension, definitely should have some interface. Correct? So let us write this. Okay. So surface tension is a binary property. Means basically this surface tension is due to imbalance between cohesive and adhesive forces. Correct? This is what we see. Now see carefully. So we have this only at the interfaces whenever there is some imbalance between cohesion and adhesive forces. So binary property, why this is a binary property? Because if there is only one fluid in consideration, definitely we don't have any surface tension. And generally if you see the values of surface tension for water air interface at 20 degrees Celsius around, this is equal to or near to 0.073 Newton per meter. And you know the units of surface tension are nothing but Newton per meter because force by length. So Newton per meter. So this is what we can write here. So sigma of a water interface at 20 degrees Celsius is 0.073. Now please tell me one thing. If I increase the temperature of the liquid, what happens to this surface tension? Will it increase or decrease? Let us suppose I have some bulk of liquid and now I am increasing the temperature of this liquid. So please tell me whether the surface tension will increase or it decreases. Any idea? Any idea? So please tell me, if you are trying to increase the temperature of this liquid, will the surface tension forces will increase or decrease? Increases or decreases? They'll ask you in few exams. If your temperature is increasing, your surface tension will increase or decrease? It will decrease. Correct? Because it will decrease. Look, why? Because cohesion forces gets decreased. Correct? We have seen this in case of viscosity as well. Both viscosity and surface tension are also because of these cohesive forces. But of course, in case of surface tension, we have the cohesion forces, adhesion forces because of an external fluid as well. Correct? But if you heat the substance, if you heat the liquid, then what happens? Your molecules start, they tend to move, and of course, these cohesion forces starts decreasing, which means here in this case, these forces which they are pulling decreases, which means this F decreases. Is that clear to all of you? Is that clear? Because these molecules which are strong initially to pull this molecule which is here, now they don't act that much strong because they tend to move in their own direction. Is that clear to all of you? So as temperature increases, your surface tension decreases. Correct? So you can write this point as well. So as temperature increases, surface tension decreases. I hope all of you are clear with this, correct? This is the reason why it happens. I'll tell you. In home, normally when our clothes are too dirty, then they are supposed to be soaked in a hot water, correct? What does a hot water do better? Okay, normally if you soak the cloth in the cold water, and of course if you are soaking the cloth in another hot water, then what is the difference in between both the cases? In cold water, generally the surface tension is a bit high. Means generally you can see carefully, whenever you try to put your cloth or if you soak your cloth in a cold water, and if you take out, you can clearly see there is a layer of fluid that's getting stick there, correct? But of course when you heat the water impinges into the clothes, because basically if you are having some clothes, if this is some cloth, then there are pores inside your cloth, correct? Means there will be some dirt that is getting sticked inside, somewhere here maybe and somewhere here. Okay, now initially what happens when your water temperature is cold, and if you are soaking this cloth in a wet, if you are soaking this cloth in a cold water, then the surface tension is high, which means this surface tension doesn't allow the molecules to just touch this dirt individually, because all molecules are stacked together and they go stick as a layer, but individually molecules doesn't attempt to move inside this block. But when your temperature increases, this cohesion forces decreases and the surface tension of the water decreases a bit. Okay, so when the surface tension decreases, definitely the cohesion is weak. So that means water molecules have the power now to just go and adjust into this blocks individually. Yes, all molecules tend to act down, but similarly the forces on the surface will stretch it. Okay. Look, Vamshi, simple idea. If there is a polythene bag here, and if I am pulling this from all the sides, let us suppose I am pulling this vertically and also in all the other directions, then my hand, which is initially here, will stretch like this, correct? Which means this layer is in tension. Okay. Fine. So this is why we generally soak some over dirty clothes in some hot water, because increasing the temperature of the water reduces the surface tension, thereby increasing the molecular momentum of water molecules. So they get easily displaced into this pores and they get in touch with the dirt. And of course, when dirt gets touched in water, it gets moved out by the water. Is that clear? Did you all get the idea why this dirty clothes are soaked in hot water? Yes. So please do respond. Did you all understand what happens actually when you soak a cloth in a hot water? What does a hot water do better as compared to the cold water? Because of the free molecular movement, at least, so the molecules will impinge onto this pores and they'll carry out the dirt that's having here. Okay, clear? Good. So these are the cases of a few cases of surface tension actually. Now there is one more thing, one more very important consequence of surface tension which people may ask you in some cases, and the important consequence is why raindrops are spherical. Why raindrops are spherical? Generally when it's raining, you can see any drop. Normally if you have any drops in general, those drops will be circular, correct? Why this happens? Why they are spherical? Any idea, friends? Of course, since I am teaching surface tension, your answer will be surface tension, I know. But any clear idea why that happens? Why raindrop or any liquid drops generally, if you are pouring, why drops are spherical in general? Any idea? Due to surface tension. Yeah, this is what I told you. Because I am teaching surface tension, you guys will tell due to surface tension. I know this. Madan Kumar. So what's the meaning beyond that? Means how surface tension is affecting the size or shape. Of course, it doesn't affect size much, but of course, how it's affecting the shape of a liquid. Because PR has least surface area for same volume. Okay, good. Look, normally let us suppose this is your shape of a raindrop initially. Let us suppose. Okay. Now, whenever this liquid individually is traveling in some air, then definitely there is some interface. You can see here, there is some interface here. In this, correct? Now, if you take this locality, for example, then yeah, pressure differences and all come is surrounded by forces acting. Yes, good. So definitely, if you take this locality, then because of the surface tension here, this surface is subjected to stretching, correct? Means if there is some irregularity in the surface, then this surface is subjected to stretching, and this actually the surface which is initially like this, when it gets into the atmosphere, it gets a smooth circular shape. Correct? Because of stretching that's happening because of the surface tension effects and due to the imbalance of cohesion and adhesive forces at these two locations. Similarly, if you take this into consideration, definitely this molecule which is initially like this, it will also get circular in shape because of this again stretching of the surface. So finally, if you keep on stretching continuously, you will attempt yourself to end up in a sphere. Okay, so that is the reason why these raindrops are also spherical. So let us try to emphasize this. Because of imbalance in cohesion and adhesion forces acting on the surface of a liquid, then what happens? The external surface gets stretched, and of course this stretching happens locally at every location of this surface of water top, and finally they end up forming a sphere. Did you all get the clear idea how these drops are becoming spherical? Means initially if you are having some drop like this, then definitely because of some imbalance in the cohesion and adhesive forces at this location which is initially of this form, if you see, let us suppose this location which is initially of this form, something like this, it gets stretched. Correct? So this gets stretched in this shape, and this stretching happens locally at every position, and of course there should be also the continuity of the system. Then definitely this local stretching together, they will put up a sphere, and of course you know sphere has the minimum surface area, so work done will be always minimum for the stability, and you know for stability the energy of the system should be minimum. For stability, the energy of the system, it should be minimum. And what is the surface energy that we are doing? The work done by encasing this surface. So this work done because of imbalance. Look, that is what it's happening. So if there is some imbalance, then this surface is completely subjected to the surface tension. So when there is surface tension, similarly here in this diagram, let me show you. When there is some surface tension which is trying to pull this, then definitely this surface is subjected to stretching. Like how this surface, you know, surface here, this is subjected to stretching here, correct? So we can see there is this stretching of this surface actually, but of course it's very minute in case of very large layers, but of course in case of droplets and all you can see it clearly. Now if this is the case, then see here, this energy should be minimum, and you know surface energy is nothing but work done. And this work done is nothing but sigma into area in this case. Okay, so for this A has to be minimum for the stability. Okay, this A has to be minimum. For A to be minimum, and for any given volume, you also know mathematically that for any given volume of solid, for having the minimum surface area, the solid should take the shape of a sphere. Correct? So these are the main reasons why these raindrops are spherical. This local stretching happens, and of course all this locally stretching, if you continue throughout the path, then definitely for the whole solid, definitely this area, surface area has to be minimum, because this surface energy has to be minimum. Okay, because for the stability of the systems, you know, energy of the system has to be minimum, and definitely that's why for minimum area of a given volume, you will get a spherical shape. Is that clear to all of you? Is that clear to all of you? So please do respond. Did you all understand why these raindrops are spherical in actual practice? Yes? I need responses from all of you. Yes? Okay? Fine. Clear? Second 4335, Shubha, Madan Kumar and all. Okay, good. So now, let us see one very important equation. In your exams, Rahul, very good. So see here. In your exams, you will be facing many questions like if there is a raindrop, what is the pressure difference between in and out. Similarly, if you're having a liquid jet, what is the pressure difference between the in and out of the liquid jet? Similarly, if you're having some soap bubble, what is the pressure difference between in and out of the bubble? So there are many questions in this case, correct? So let us do some quantitative analysis for these things. Is that clear to all of you? Look, let us suppose there is some bulk of fluid. Okay, and we have taken one strip out of that fluid such that, let us suppose the strip shape is something like this. And this radius is R1, for example. Okay, and finally, let us suppose this radius is R2. Let me try to draw this a bit neatly. So this radius is R2. Okay, let us use a different color for dimensioning as well. So this is R2, and let us suppose this is R1, and let us suppose this is your horizon O. Now this is one surface actually, which is free surface. Of course, there is some air here on the top, and of course there is some liquid here. Of course, so if from a big bulk of fluid, you are taking some slice at a top. So many times you will be cutting your watermelon like this, and you will be taking out some strip, correct? So this is something like that. Can you all sense this, that there is some strip here? Yes or no? So please tell me, can you all sense that there is one such watermelon strip which we are taking? Yes or no? So please tell me, can you all recognize that there is some watermelon strip that we can take out like this from this free surface of this liquid? Let us suppose this is the small area which I am taking, so I am just enlarging this. Okay, now see carefully what happening. There will be some internal pressure that's acting on the fluid. Let us change the color. So yes, let us suppose there is some internal pressure that's acting on the surface, and similarly let us suppose there is some external pressure that's also acting on this surface. So this is P outer, and this surface here which we have, this pressure which we are having here is P inner. Now see carefully, from this bulk of fluid, if I am taking the surface, definitely this surface is subjected to some forces, surface tension forces, correct? Let us suppose this is air somewhere here on the top, which is acting on this complete surface. Now whenever I am taking this block out, if I draw the free body diagram of this block, if I am taking this block out, and if I am drawing the free body diagram of this, then definitely there will be some surface tension forces that are acting on this, correct? So let us summarize this surface tension force. Let us summarize this surface tension force. This is something like this. Similarly, on this surface as well, there will be some surface tension force that's acting here, correct? So what will be the value of this surface tension force on either faces? Look carefully. If this is sigma into, now what will be the surface tension force on this side? Same will be the surface tension force on this side as well, correct? Because they are symmetric actually. So this is sigma into what? Let us suppose this angle which you are making here is d theta 1, and this angle which we are having here is d theta 2, correct? So this small angle which we are having here is d theta 1, and similarly this angle is d theta 2. Now this is sigma into, now what is the length of this face? Length of this face, look, if this is R2 and if this is d theta 2, then can I write the length of the arc is nothing but radius into this angle, L is equal to r theta. So if you are having some circular sector, then definitely the length of the arc is nothing but L is equal to r theta. So since the force is nothing but surface tension force into the length on which it is acting, so definitely you can write this as R2 into d theta 2. Are you all clear till here? Did you all understand why this surface tension force acting on this layer of the fluid is sigma times R2 into d theta 2? Yes or no? Similarly, this will also be sigma into R2 d theta 2. Correct? Yes or no? So please do respond. Yes? Similarly, yes? Can you all understand this? Why this is sigma into R2 d theta 2? Because this length is R2 and this small angle here is d theta 2. So this is R2 into d theta 2 is the length of this surface, and length in sigma is the surface tension force per unit length. So sigma into this length will give you the total force that is acting on this layer. Correct? Similarly, sigma into R2 d theta 2. If that is sigma into R d theta 2, then can you please tell me what will be these forces that are acting here? Can you tell me what are these forces that will be acting here? This is sigma times R1 d theta 1, and this will also be sigma times R1 d theta 1. Correct? These are the different forces which are acting on this fluid block that you are taking out. So if you are taking a small block of a small slice of fluid, then these are the complete forces which are acting on this fluid slice. Yes or no? Are you all clear till here? Of course, weight will also be there, but we are neglecting weight for the time being. So please tell me, if these angles are very small, the volume is very small, so we are neglecting the weight for the moment. But of course, please tell me, can you identify that these are the total forces that are acting on this fluid size? Yes? So do respond. Correct? So these are the total forces that are acting on the fluid slice. Now, let us try to apply the free body, force balance of the free body diagram. Of course, this is the free body diagram of the slice. So once let us try to identify what are the forces in particular directions. Look, if you see this slice in this direction, look, we are seeing this slice in this direction. If you see this slice in this direction, look, I am trying to plot here. Let me try to plot this. So this is your arc, and you have your slice, something like this. Okay, now there is surface tension force. There is surface tension force along this edge, which is sigma times. If you are looking from this edge, you will be able to see this force and that force which is acting here. Okay, so sigma into R2 d theta 2. Similarly, sigma R2 d theta 2. Okay, this is the force that are acting here. Now, if you know that this complete angle is d theta 1, if this complete angle is d theta 1, then you know this is half of this. So this angle will be d theta 1 by 2. So d theta 1 divided by 2. Now, if you resolve these forces into horizontal and vertical directions, look carefully. Let us try to resolve that. If you are resolving these forces in horizontal and of course vertical directions, now see carefully. Resolving this horizontally and resolving this vertically. Okay, resolving this vertically. Similarly here, resolving this horizontally and resolving this vertically. Now see carefully. If the angle between the vertical and this is d theta 1 by 2, because you know this is d theta 1 by 2 and this angle is also d theta 1 by 2, then please tell me, if this angle between the normal, this vertical and this angle is d theta 1 by 2, then can you please tell me that the angle between this plane which is perpendicular to this and this horizontal, means this one will also be d theta 1 by 2. Correct? Similarly here, d theta 1 by 2. Can you all understand that these two angles are d theta 1 by 2? Yes, these are the forces because of surface tension. Correct. Correct, Vamshi. So, can you identify that when you are seeing this fluid from this liquid, from this direction, then this is what you have. This surface is this surface, and sigma R2 d theta 2 is what you can see on the sideways, and we are resolving this. Correct? Similarly, if you try to resolve this from this point of view, look carefully. We have the surface again, and this angle here is d theta 2, and now when you are looking from this angle, you can see this sigma R1 d theta 1 and sigma R1 d theta 1. Correct? So let us write this sigma R1 d theta 1, and of course this is also sigma R1 d theta 1, and this angle is d theta 2. So half of this will be d theta 1 by 2. So this angle is d theta 2 by 2, and of course this angle is also d theta 2 by 2. Now if you resolve these two forces again, look, it's very simple actually, but trying to remember the formulas will make the life difficult. Okay, so that's why let us attempt this. Okay, next, similarly here and also here in this resolution. So now you can see clearly this angle is nothing but This, if this is d theta 2 by 2, then this angle is also d theta 2 by 2 and this angle is also d theta 2 by 2. Now, finally, let us try to understand one thing. This horizontal component will be balanced by this horizontal component, correct? Because these two horizontal components are same. Yes. Similarly, this horizontal component will also be balanced by this horizontal component. Means because of this surface tension forces, there are total 4 components of vertical force that are acting on this slice, which are nothing but sigma r2 d theta 2 into the vertical component of this force. Similarly, second one here, sigma r1 d theta 1's vertical component and also this. So if you apply the equilibrium of this slice, can you understand that there are total 4 forces of surface tension which are trying to pull the surface down? Yes or no? Please tell me, if you look at this diagram, can you all identify that there are total 4 components of this surface tension forces which are trying to pull this surface down? Correct? Yes or no? Can you all understand this? There are total 4 components of this surface tension forces which are trying to pull this block down. Yes? All of you. I need responses from all of you because these horizontal forces, they get balanced to each other. So which means there is one force, second, third and fourth. These are the 4 forces which are trying to pull this surface down. Correct? So let us write equilibrium. So this force is sigma r2 d theta 2 and this sine component of that. Okay. So sigma Fy is equal to 0 implies sigma r2 d theta 2 into sine d theta 1 by 2. Sigma r2 d theta 1 by 2. Sorry, sigma r2 d theta 2. Okay, fine. Sigma r2 d theta 2 into sine d theta 1 by 2. And of course, there are 2 components on either side, correct? So there is one component here and also there is another component on this side. Similarly, for this we have sigma r1 d theta 1 into sine d theta 2 by 2. Look, plus sigma r1 d theta 1 into sine d theta 2 by 2. And of course, these are also 2 forces. Correct? We can have this 2 finally. And this should be equal to, look, now this is the complete vertical force that's acting on the surface to pull it down. Now by what forces this is compensated? Look, this P1 is, this P inlet is acting in the upward direction and P outer. So can we write this is nothing but P inlet minus P outlet into this area. Since this area is very small because this slice which we are taking is very small, then can we approximate all these as straight lines? If we approximate all these as straight lines, then this is something similar to rectangle and this length is r1 d theta 1 and this length is r2 d theta 2. So can we write the area of the curved surface as r1 d theta 1 into r2 d theta 2? Can we write this? Look, things are very easy. It's only identifying forces. That's it in a correct way. Is that clear? Are you all clear? How did we write this equation? Are you all clear till this moment? How did we write this equation? Are you all clear till this moment? How did we write this equation? Yes or no? So please do respond. Are you all clear till this point? Okay. Now, for small theta, for small values of theta, you can write one thing, your d theta 1 by 2 is equal to sine d theta 1 by 2 because for small values of x, sine x is equal to x, and similarly d theta 2 by 2, this is always equal to sine d theta 2 by 2. Correct? This is what we can write. Right hand side, how I wrote? Look, inlet pressure is acting on top direction and of course outlet pressure is acting on the in the bottom direction. So P inlet into this area minus P outlet into this area is the right hand side. Okay, so which I have written P inlet minus P outlet into this area. So if you substitute these approximations in this equation, look, what do we have? Sigma times R2 d theta 2 into d theta 1 by 2. Look, this sine d theta 1 by 2 which is here, I am using this approximation, into 2, we have a 2 plus sigma R1. Okay, sigma is taken out as common. So R1 d theta 1 into d theta 2 by 2 into twice of this is equal to P inlet minus P outlet into R1 times R2 times d theta 1 into d theta 2. This is what we have, correct? So this is the complete equation. So one thing is very clear, you can cancel these 2's, and if you cancel these 2, then we can have this d theta 1 into d theta 2 as common in all the terms. So let us cancel this d theta 1 into d theta 2. So from this, what did you observe? Look, we are getting one equation that the difference inside the liquid and out means if there is some bulk of liquid, the pressure difference between this liquid at this point and at this point means the difference between this P in and P outlet. This is nothing but P inlet minus P outlet. This is nothing but, look, sigma is common out and you have R1 plus R2 divided by R1 R2. Can we write this as 1 by R1 plus 1 by R2? This is the case, or this is the generalized formula for identifying the pressure difference inside any liquid body or fluid body. Is that clear? This is the equation. So this is P inlet minus P outlet is equal to sigma into 1 by R1 plus 1 by R2. Look, it's only 2 steps, first step and second step, just simple approximations. But the only thing that lies is in identifying these forces. Is that clear to all of you? Can you all identify that this slice is nothing but the exaggeration of this small slice that I am taking? Yes or no? Is that clear to all of you? Did you all identify that P inlet minus P outlet is sigma times of 1 by R1 plus 1 by R2 in this case? And if you remember this formula of sigma into 1 by R1 plus 1 by R2, this is very much helpful for you. And this is of course for the case of droplet, because in case of droplet, what happens? In case of droplet, what happens? There is only one phase surface. But if you take the case of bubble, then in case of bubble, what happens? The bubble has some thickness, and if there is air here and also air here, then there will be one surface tension on this force, and also there will be another surface tension on this second surface. So this complete formula will get multiplied in case with 2 here on this side, correct? So are you all clear till this point? Are you all clear till this point? This is a big derivation. It appears to be big. It takes some time, but of course, it's really a very nice thing that we could remember this formula, sigma times of 1 by R1 plus 1 by R2. Now, based on this, we will see what are the pressure differences inside a liquid droplet, again inside a basically some soap bubble or some liquid film bubble, and also in a liquid jet. Is that clear to all of you? Second, Shubha, Rahul, all of you. Good. So now, this is the case of a droplet. So per droplet, this pressure difference P inlet minus P outlet is equal to sigma times of 1 by R1 plus 1 by R2, correct? And of course for bubble, because I have shown you, for bubble, this P inlet minus P outlet will be equal to, look, here you will be getting 2 times of sigma, correct? Because there will be 2 forces that are acting on 2 different interfaces. So definitely you will get some 2 in multiplication of the sigmas, and there sustains a 2 on the left hand side. And finally this formula appears to be 2 sigma of 1 by R1 plus 1 by R2. This is what you have. So are you all clear till this point? Are you all clear till this point? If this is the case, now let us consider few cases. A, for liquid droplet. Even this question was asked in GATE 2021. So let us observe the things. For liquid droplet. So whenever you are having a liquid droplet, there is only one interface, which means we'll use the first formula. And for a liquid droplet, this is spherical and it's also symmetrical. So this R1 is equal to R2. So first liquid droplet, R1 is equal to R2 is equal to R, correct? Because for a liquid droplet, if you take some strip, then definitely both the radius will be same. So this R1 is equal to R2 is equal to R. So this implies your pressure difference P inlet minus P outlet, and always inlet pressure will be higher because it's quite common. You can see there is a convex convex bulge of the liquid droplet. Means let us suppose this is initially flat. If this pressure inside is more, then definitely it will take it gets this shape, and of course there is some convex shape on the top, and this is the reason why inlet pressure is always more. Okay, sometimes they give you this outlet pressure as air and they ask you for gauge pressure. Of course, in second chapter, which we are going to start from Monday, so in fluid statics we will see what is this gauge pressure and vacuum pressures. But for the time being, this P inlet minus P outlet is equal to sigma into 1 by R plus 1 by R, because R1 is equal to R2 is equal to radius, because P is symmetrical. So this is 2 sigma by R. Okay, this is the case. For liquid jet, look, what is the case of liquid jet? If you are having a liquid jet like this, then there is some radius R1 in this case. But of course, if you keep on stretching this, this becomes a jet of continuous diameter. So if this is radius R, then if this is your infinitely extending length of the jet, then you can see your R1 is nothing but R. And if you want to have the continuity of the jet, then this radius, second radius R2 should keep on extending, which means this R2 should tend to infinity in this case, correct? So basically in a drop, if you try to keep on stretch that, then after maintaining some certain diameter, if you are having still extension, then this second radius is going to be infinity. Are you all clear how this R1 is equal to R and R2 tends to infinity in case of a liquid jet? Because if you keep on stretching this bubble, then what happens? If you keep on stretching this drop, then you, after getting some fixed diameter, this keep on extending and you will be having a continuous strip of liquid jet. So are you all clear how this R2 tends to infinity in this case? Yes or no? Are you all clear how this R2 tends to infinity in this case? Yes? In this case, R1 is equal to R and R2 tends to infinity. So this implies your P inlet minus P outlet is equal to, means P in minus P pressure outside is equal to sigma into 1 by R plus 1 by infinity. This is equal to sigma by R. This is what we can see here, correct? So the pressure difference inside a liquid jet is nothing but sigma divided by R. And of course, pressure difference inside a liquid droplet is nothing but 2 sigma by R. Now for droplet, if you are having 2 sigma by R, then for bubble, what it could be? Any idea? For a bubble, even bubble is spherical and it's symmetric. So R1 is equal to R2 is equal to radius of the bubble. So can you please tell me, for in case of bubble, this 2 sigma by R can be replaced with? For case of a bubble, this 2 sigma by R can be replaced with? So please tell me, in case of a bubble, this 2 sigma by R can be replaced with? Or can you please tell me, this 2 sigma can be, this 2 here can be replaced with which number? This 2 here can be replaced with 4, correct? 4 sigma by R. So let us write that for soap bubble or for liquid, for bubble you can write for bubble of radius R, for bubble of radius R, this delta P, which is this P inlet minus P out, P internal minus P outer, this is equal to, correct, P internal minus P outer is equal to 2 sigma times of 1 by R plus 1 by R, which is 4 sigma by R, correct? And this is what exactly they asked in GATE 2021. Inside a soap bubble of radius R, what is the pressure difference? So 4 sigma divided by R. So are you all clear till this points? Are you all clear till this points? Yes? Yes or no? So please do respond. Are you all clear till this points? Did you all understand the standardized formula for identifying the differences between pressures in liquid jets, soap bubbles and all? Mansingh, you are late for today's class. Clear? So we had a clear equations, how these equations come because of just some pressure balance that we are applying, some force balance that we are applying on taking this elemental slice. Okay, so if this is your elemental slice, exaggeration of elemental slice, then these are the forces that are acting, and if you apply sigma Fy is equal to 0, this is what you will be having. Clear? Yes? Okay, then so okay, so as I told you, okay, let us end this lecture here for the time being because we had some interesting things today. So are you all clear why this raindrops are spherical? First of all, because in few interviews they ask you this. Why raindrops are spherical? Because of the surface tension forces and surface energy that is involved for a given surface. I mean, for a given volume, the surface area will be minimum in case of a sphere. And why the surface area has to be minimum? Because if the surface area is minimum, only in that case the surface energy is minimum. Okay, which includes, strongly supports the stability of the liquid droplet. So definitely the raindrops has to be spherical. Similarly, why dirty clothes are soaked in hot water? Because increasing the temperature of the water reduces the cohesion, which means the surface tension forces decreases, and of course they get easily sticked onto the, they get easily impinged onto the pores of the clothes. This is what we have seen, correct? Then, are you all clear about these two formulas that we have obtained? So tomorrow, coming to tomorrow's class, we will deal a bit of consequences of surface tension like capillarity for some time, and also we will solve some questions on this complete chapter, fluid and its properties, because tomorrow is going to the closing lecture of this first module. After dealing capillarity, we will end this lectures on first module. So we will practice some good questions, but there is some small change, so please do listen. What is that change? Our lecture is not on YouTube. Okay, this is not on YouTube. It is for free. It is for free, but it's not on YouTube. This lecture is going to be on the Infinity app. Okay, as we were telling you, as you could see in the Play Store, I'll tell you how to have an idea on this also. So see here, if you go to Play Store in your mobile, of course that is Google Play here. So let us show you. If you go to this Google Play, means Play Store basically in your app, in your Android mobile, then definitely in this search you can search this Infinity-Hub. Infinity-Hub. So if you search this Infinity-Hub, let us click one more I here. So Infinity-Hub, then you can clearly see this is the app that is launched by Engineers Hub, correct? This app we have launched, and also some XC test series and also some other test series were also launched on this app. So you need to install this app, and of course the class is on this app for tomorrow. Okay, it's not on YouTube. Is that clear to all of you? Is that clear to all of you? Where is the class? It's on Infinity app, but not on YouTube for tomorrow. We have practice problems, problem solving session on this app tomorrow, and of course we'll solve many problems that are basically dealing with all the concepts that we have discussed so far, and which are also some previous year gate questions. Is that clear to all of you? Clear? So tomorrow's lecture won't be on YouTube, and of course the timing will be same, 9:30 p.m. to 11 p.m. I told you that changing timing is subjected only for today. So from tomorrow we have the as usual timings, 9:30 p.m. to 11 p.m. Is that clear? Timing is 9:30 p.m. to 11 p.m. and the location where you can find this is on Infinity app, but not on Engineers Hub YouTube channel. No, regular class is not on app. We are going to deal it on YouTube, but of course few sessions we are going to conduct few problem solving sessions, and of course few important sessions we are going to talk this. So in gate mechanical, the laminar flow question of fluid mechanics, when he asked about average shear stress, we have to take average velocity inertia, which is 40, but in gate it's 80. Look, I think the calculations are a bit correct, but even I strongly believe 80 pascals is the correct answer. Okay, because if you apply this Newton's law of viscosity, tau is equal to mu into du by dy and all, and of course if you substitute at the wall, the answer is 80. Okay, he also told along with average shear stress, he also asked at the wall, so definitely it's 80. Okay, anyhow, that is at the wall, it's not of the complete section. Okay, Ramkrishna, fine. So see here, so this is the place we are going to have this tomorrow's session. Okay, and of course if you're liking the content, please do like the videos, and if you're on this channel, please do subscribe to the channel. Okay, and also let us quickly go through the future events that we are having. Yes, tomorrow we are having this problem solving sessions on Infinity app. Of course, I told you good enough. And on 7th, on 6th of March, means tomorrow at 7 p.m. you are having an event on YouTube that how this IIT Bombay is how this unexploring IIT Bombay, means basically what are the resources available at IIT Bombay will be open to you by these two IIT Bombay alumni like the VS sir, and Negi sir. Okay, so this event is tomorrow sharp at 7 p.m. on this channel, so you can attend this event, and once this event is done, we'll be having the problem solving session on the first chapter on Infinity app. Clear? And once this is done, then these are the batch details that we have started, and this is offline batch actually. Okay, so we have started offline classes of Engineers Hub, which I have shown you the classroom, something like this. So if you feel that you can find some seat here, definitely you could immediately do that. And of course first batch we have started at 1st of March, and of course that batch is running successfully, as you know. And of course the second batch we are going to start is at 15th of March. Okay, so on 15th of March we are going to start a second batch for this regular, and the class timings will be 2 p.m. to 7 p.m. and this batch generally sustains for 5 to 6 months. for the coverage of the syllabus. Okay, and the final batch we are going to start on 29th of March. So this is a 5 to 6 month exclusive program for passed out students, and also if some final years whose projects are going on, if they want to attend, they can also attend this. But this batch will be personally mentored by Negi sir and of course his faculty team. So definitely you will get some good knowledge and subject levels out of this. Okay, so this is our classroom picture as I have shown you, and these are our official contacts. You can always find some useful content on this Engineers Hub YouTube channel. So if you are on this channel for the first time, please do subscribe to the channel, and if you're liking the content, please do like the videos as well. Okay, and this is the official Telegram channel of Engineers Hub Mechanical, and we are posting these notes on daily 2 platforms, this Engineers Hub Mechanical group and also a mechanical channel, and also this Engineers Hub all other gate branches channel. So basically just to avoid traffic, we have kept mechanical as separate and all others as separate. Okay, and of course all the official websites of Facebook, I mean all the official updates of this Engineers Hub can be found in the Facebook My Engineers Hub page, similarly LinkedIn profile, and also our official website engineers-hub.com. okay, and also this is our Twitter account where you can find some lot of interesting facts and some day-to-day questions for practice. And also in Infinity app we are having some section for daily practice problems and also a weekly test. Okay, so on Thursday there is some weekly test. On every Thursday between 7 p.m. to 8 p.m. you can start a weekly test which is based on the syllabus that I cover throughout the week. Okay, so is that clear to all of you? Are you all clear about tomorrow's class timings and the venue of the class? Yes? Fine? Is that clear to all of you? Okay, so is that clear? I need responses from all of you. Okay, then very good. So please don't miss tomorrow's class, because tomorrow we'll be solving problems based on all these topics which we have covered. Okay, so thank you all. Have a nice time. Good night.